Hello, everyone. Welcome to Math Made Simple by Professor Burnett. For my MAC 1105 College Algebra class, I will be reviewing Section 4.6, Polynomial Inequalities. Let's get started with problem number 1. Here we have the quantity x plus 6 times the quantity x plus 2 less than 0. So we will be solving for the solution set and placing the answer in both interval notation and graphical form. So we need to start by finding our critical values. We're going to be using the zero product property, which states whenever you have two factors multiplied together and the product is 0, one of those factors must have been 0. One or both must have been 0. So let's just analyze the problem first. And this inequality symbol does not involve 0. So I know the endpoints will be open. Okay? And when a quantity is less than 0, that means numbers smaller than 0, those numbers will be negative. So I'm going to be looking for regions on the number line that result in a negative quantity. So let's set each quantity equal to 0 and solve for x. So x plus 6 equal to 0, or x plus 2 equal to 0. And it doesn't matter at this point that there is no option equal to 0 in our inequality. The point is we're trying to find our critical values, so we will let them equal 0. Now we have two separate equations, and we're going to solve for x. To get rid of plus 6, we are going to subtract 6. And what I do to one side of the equation, I'm going to do to the other to maintain balance. Subtract 2 from both sides in the second equation. And I get critical values of x equals negative 6 or x equals negative 2. Now, we are going to graph these critical values on a number line. And we have to make sure they're in ascending order. So negative 6 and negative 2. So that's going to create, those two critical values create 3 sections on the number line. And so now, because we know that the endpoints will be open, we're going to put open endpoints on the critical values. And now we need to test whether we're going to get a positive or negative result in each of these 3 intervals. So we're going to need a number other than these critical values. 0 is always a good number, an easy number to test. In between negative 2 and negative 6, we can try negative 3. And to the left of negative 6, we will try negative 7. And remember, we are plugging this into the original inequality. So testing negative 7, and I'll write this one out completely. Substitute in for x negative 7, and we get negative 7 plus 6 times the quantity negative 7 plus 2. And we get negative 1 times negative 5. And basically that's going to be a positive 5. From here on out, we're just going to be concerned with, are we going to get a positive or negative result? So we'll be listing a negative times a negative. That's going to give us a positive in this region. And that is not what we're looking for. We're looking for the negative region or regions. And generally, these regions alternate. So if we started with positive here on the left, I expect a negative in the middle and a positive on the end. But we're going to test now with plugging in -3. So -3 plus 6, 6 minus 3, that's going to be a positive. And then -3 plus 2, that's going to be a negative. 2 minus 3 is a negative. A negative times a positive is going to give me a negative. For the final region, we plug in 0. 0 plus 6, positive. 0 plus 2, positive. So this region gives me a positive. And remember, I want to shade the negative region. And that would be this region here, in between the two endpoints. So that is the graphical form of my answer, my set of solutions. And now interval notation would be an open interval, -6, comma, -2, and an open endpoint as well. So an alternative way of graphing this we have open endpoints, and we can graph this way, okay? So that's problem number 1. Let's move on to problem number 2. Problem 2. X squared minus 12.5x is greater than 0. So I notice that I can factor out an x. So I'm going to do that. And I'm left with x minus 12.5 greater than 0. So now, again, the zero product property tells us I can set each one of these quantities equal to 0, then isolate x. And so x is already isolated at x equals 0. And for my second equation, I'm going to add 12.5 to both sides of the equation. Arriving at x equals 12.5. So these would be my two critical values. So I will sketch a number line and include 0 and 12.5. Again, we have an open endpoint, and this time numbers that are larger than 0 are positive numbers. So we test our intervals. We can start with the original inequality or the factored form, okay? We need to test numbers other than our critical values. So I'm going to test 1. That's an easy number to test. I'll test -1 and 13. And when I plug it back in to the factored form, I get -1 in place of x and -1 minus 12.5. That's going to give me a negative times a negative, positive region. When I test 1 in for x is going to give me a positive, and then 1 minus 12.5, that's going to give me a negative. This region will be negative. Testing 13, replace x with 13, that's positive. And then 13 take away 12.5, that's going to be positive as well, making this region positive. And that's exactly what I'm looking for. I'm looking for the positive region or regions, and that happens to be 2 of them, the left and the right. So I'm going to shade all of those answers less than 0 and greater than 12.5. So that's 2 intervals, and we're going to list it like this. From negative infinity up to 0, but not including 0. Unite that with this other interval from 12.5 throughout positive infinity. So we have our interval notation as well as our graph of the solutions. Now for problem number 3. Six x squared plus 72 minus 42x is greater than or equal to 0. Okay. Now, this is a trinomial, and it is not in descending order. And I know that by looking at the powers on x. 6x squared minus 42x to the first power plus 72x to the 0 power. Anything to the 0 power is 1. So we have our constant term. So placing this polynomial in descending order, we get 6x squared minus 42x plus 72. All greater than or equal to 0. Now, I notice that each one of the coefficients in every term is a multiple of 6. So I can factor out a 6 from each one of these terms. Factoring out is akin to dividing out. So basically, factor out a 6 from each one of these terms, and that's going to go out front. And what remains is x squared, because 6 divided by 6 is 1. 1x squared is just an x squared. 42x divided by 6, subtract 7x. And the constant 72 divided by 6 gives us 12. All greater than or equal to 0. And now I want to factor this polynomial. X times x is my choice, one and only choice for the first term. And the last term I have choices 1 times 12, 2 times 6, and 3 times 4. Using my sign rules, I'm looking for factors, these pairs of factors that add to 7, okay? And so that would be my 3 and 4, and this is the only choice up front. So now when I factor, I get 6, and I get ready for my 2 binomials. X times x, first times first. We're going to place our 3 and 4. And now finishing up with our sign rules, a plus on the constant term means both signs are going to be the same. And same could mean both negative or subtraction in the middle of the binomial, or both addition, but they're going to be both the same. We look to the sign on the middle term to see how they're going to be the same. That's a subtraction sign. So that means they're going to be the same in this way. So we place our subtraction symbols. Okay? So now we have thoroughly factored this trinomial. And now we get to use the zero product property. We have three factors now. We have a 6, we have the quantity x minus 3, and we have the quantity x minus 4. This 6 is a constant number. It tells me nothing about x. There's no variable attached to that factor. But we can try. We set each one of the factors equal to 0, and we right away see that 6 does not equal 0. Or the second factor, x minus 3 equals 0, or the third factor, x minus 4 equals 0. And we isolate x. No x here in the first term. We're going to add 3 to both sides of the equation to isolate x. And in the last case, we're going to add 4 to both sides of the equation to isolate x. Okay. So now that brings us to x equals 3 or x equals 4. So those are our critical values, 3 and 4. It just so happens that they're already in ascending order, 3 and 4. Now we go back and analyze our inequality. Greater than or equal to. Our endpoints will be closed. And greater than 0, we're looking for exactly 0 or greater than 0, which means we're looking for positive numbers. So because the solution may equal 0, we're going to close our endpoints. When we plug in 3 or 4, we will get 0. Now, let's look for the positive regions. So we have to test our intervals. So we will choose numbers between 3 and 4 and beyond 3 and 4. Between 3 and 4, we are going to test 3.5. To the right of 4, we will test 5. To the left of 3, something smaller than 3 and very easy to plug in, 0 or 1. Let's go with 0. And so we're going to test at this level here. Okay, so we have a positive 6. We plug in 0. 0 minus 3, we're going to get a negative. We plug in 0 to the third factor. 0 minus 4, we get another negative. So that's going to give us positive. That's what we're looking for. Greater than 0 or exactly equal to 0. We test the middle region. 3.5. So we have 6 times 3.5 minus 3. That's a positive result. 3.5 take away 4. That's a negative result. So overall, this middle region is negative. That is not what we're looking for. We're looking for greater than 0 or exactly equal to 0. And the endpoints cover the equal to 0. And we test 5. So we have 6 times 5 minus 3. That's positive. 5 minus 4. That's positive as well. So we get a positive outcome. And since we're looking for the positive regions, These are all of the solutions. And if we write that in interval notation, that looks like this. From negative infinity up to positive 3, united with this other interval. And because there's an equal to this time, we have to close that endpoint. 4 is closed as well. So we start at 4 and we go on out to infinity. And we can't close positive or negative infinity. So here is our answer in interval notation and our answer in graphical form. And again, if you may also use this notation for the graph. Okay. Problem number 3. That was problem number 3. Let's move on to problem number 4. Negative p squared is less than or equal to negative 3p squared minus 70p. Okay. And we're going to fix this first exponent because that's actually a negative p cubed. Okay. So we're going to collect all of our terms to the left side of the inequality. And so in order to do that, we're going to add 3p squared to both sides. And let me give ourselves some more space so that I can provide more explanation. So again, negative p cubed, I'm going to exaggerate the space here, is less than or equal to negative 3p squared minus 70p. And so if we're going to collect all of the terms to the left side of the inequality, then we need to get rid of those on the right. So the opposite of negative 3p squared, so we're going to add 3p squared to both sides. And we're going to collect like terms as we go. On the left, there's no other p squared term, so we start a new column. And we're going to add 70p to both sides. Okay. So now what happens? We just get to list the 3 terms because they're all different. Different exponents on all of the variables. And on the right, the terms add up to 0. 3p squared minus a 3p squared, that's 0. 70p minus 70p, that's gone, that's 0. So we've collected everything on the left. And then now I notice what I can factor out. I can factor out a p, and I can also factor out a negative p. So I want to do that because I want to leave a polynomial leading with a positive coefficient. So Factoring out is just like dividing out. So I'm going to show my work for what I'm factoring out, a negative p. And that's going to leave me with a trinomial times the negative p. And that quantity should be less than or equal to 0. So here's what we have left. Positive p squared minus 3p minus 70. And so I can factor further. Looking at our factoring options, p times p gives us p squared. There's many different options to get 70, but looking at my sign rules, I need a pair of factors of 70 that subtract to give me subtract 3p. And my signs are going to be different. Okay? So I know that's going to be 7 times 10. 7 times 10 is the product is 70. And those factors will subtract and give me 3. So let's factor. We have our negative p. P times p. And the first terms of each binomial. And 7 times 10. If I want an outcome of subtract 3p, 10 is going to control the outcome. It needs to be subtract, and the other sign needs to be different. So now I have 3 quantities. Negative p, p plus 7, p minus 10, all multiplied together to be equal to 0 or less than 0. So we're going to go with the equal to find our critical values. And all 3 of these quantities involve the variable p. So they're going to give me information about p. So I'm going to have 3 different critical values, which means my number line is going to be divided into 4 different sections that I'm going to have to test. So let's start by setting each quantity equal to 0 and isolating the variable p. Negative p equals 0, or p plus 7 equals 0, or p minus 10 equals 0. And we isolate p. Okay? Starting in the middle, we know we subtract 7 from both sides. On the end, add 10 to both sides. So now we have p. 7 take away 7 is 0. 0 minus 7 is a negative 7. And that leaves us with p equals 10. And to get rid of the negative, we have 2 choices. We can multiply both sides by a negative, or we can divide both sides by a negative. Let's just try multiplying both sides by a negative. Negative times a negative is a positive. P, positive understood. 0 times anything is 0. So that's just like saying negative 1 times 0. 0. So these are my 3 critical values. So now we have a number line, and we need to put these values in ascending order or increasing order. Negative 7 is the smallest, 10 is the largest, and 0 is somewhere in between. So those are my 3 critical values. Let's go back and analyze our inequality. So the fact that the equal to is present means we're going to have a closed interval. And when something is less than 0, that quantity is negative. Okay, so let's deal with the closed endpoints. Let's close them all up. And if you're using interval notation, we're going to be using the brackets. Until we figure out the quantities that are negative, we won't know which direction to face these endpoints. So we'll deal with the closed dots for now on the endpoints. So now, 4 sections to test. A number between 0 and 10, easiest number, 1. Easiest number to test. To the right of 10, 11. On the other side of 0, -1 will work. And to the left of -7, we're going to try -8. So we're going to test those 4. And this time, remember what our factored inequality looks like. So this is where we are going to be plugging in our test values. Okay, so -8. We're going to plug that in into -p. So there's already a negative out there. And then we plug in the -8. Then in the middle quantity, -8 plus 7, or 7 subtract 8. That's going to be a negative result. And in the last quantity, -8 minus 10, that's a negative quantity. So 1, 2, 3, 4, we have an even number of negatives being multiplied together. That's going to be a positive. Because here, a negative times a negative is a positive. Here, negative times a negative is a positive. Positive times positive is a positive. So this region is positive. And according to our inequality, we're looking for negative outcomes. So we are not looking for this region. This first region. So if my guess is correct, these regions will alternate. Negative, positive, negative. But we have to check. Sometimes we get a curveball in our polynomials and it doesn't work out like this. So we'll do a quick check and test the interval between -7 and 0. And we've chosen 1. So a negative p. So a negative times a negative for -p. And then -1 plus 7. That's going to give me a positive. And finally, a -1 minus 10. That's going to give me a negative. So I have an odd number of negatives. My outcome will indeed be negative. That's one of the regions that I'm looking for, the negative region. So I can go ahead and shade that region in. And to finish out our work, negative times a negative is a positive. Positive times a negative is a negative. So we just have to make sure we know our sign rules. Now for the third region, we're testing the number 1. Negative p, so negative times the positive 1. And then for the middle factor, 1 plus 7, It's a positive outcome. And the third quantity, p minus 10, 1 minus 10, is going to give me a negative. I have an even number of negatives. My outcome will be positive. But just to show the work, a negative times a positive times a negative, and then negative times a negative gives us a positive. We're not looking for that region. We're looking for solutions that are less than 0, in other words, positive. And we test our final region by plugging in the number 11 to our inequality. Negative p, negative 11. Okay? We're plugging in a positive 11 behind a negative. The middle quantity, p minus 7. 11, actually it's p plus 7. So 11 plus 7, that's going to be 18, or a positive number. And then finally, p minus 10, 11 minus 10, that's going to be 1, or a positive. So we get a negative times a positive, which is negative, and that's what we were looking for. So we shade these answers, and they include all of our endpoints. So how do we write that in interval notation? First, we'll go ahead and demonstrate this, since it's a little different. If your professor requires the interval endpoints, then this is how this would look. From 7 to 0, and everything in between, that's a negative region, and from 10 and greater. That makes it easy to transition to interval notation, which looks like this. All the values, including negative 7, all the way through 0 and including 0, united with this other interval, including 10 and greater, and no cap on infinity. So this is our final answer in graphical form as well as interval notation. Okay, so that leads us to problem number 5. Which looks like this. And this is a 4-termed polynomial. So, negative 2x cubed plus 10x squared plus 18x minus 90 is less than 0. So we are going to use a different strategy for factoring, and it's called factoring by grouping. So let's just separate the first 2 terms from the last 2 terms in this polynomial. And then we're going to factor out or divide out a common factor from each pair of terms. Here, I see that I can factor out a 2 as well as an x squared from both of these terms. For the last pair, I notice that I can factor out an 18 from both terms. 18 times 5 is 90. Okay, so here's what I factored out. 2x squared. That leaves me with x positive divided by a negative is a negative or subtraction. 10 divided by 2 is 5. X squared divided by x squared is 1, so that's gone. So I'm hoping when I factor out the 18 from both terms that I'm going to get x minus 5. And I want to go ahead with my record keeping and bring down the subtract, or less than 0, less than 0. So 18 divided by 18 is 1x, or simply x, minus 90 divided by 18 is 5. And so I indeed have x minus 5 on both sides. So that means I'm going to factor out now x minus 5. So since we have that in common, I'm going to divide or factor that out. And that's going to leave me with two factors. Negative 2x squared plus 18, understood here, and x minus 5 is less than the 0. And I notice that I can factor further a negative 2. Factor out a negative 2 from the binomial factor. So let's factor that out. And that leaves me with x squared minus 9. And I notice that that is a difference of 2 perfect squares times the quantity x minus 5 less than 0. Okay? So x times x, 3 times 3, those are the perfect squares. And we factor. Negative 2 times the quantity x plus 3 times the quantity x minus 3 times the quantity x minus 5 is less than 0. Okay? And so the zero product property says if you have these products, these factors multiplied together and the product is 0, then one or all of the factors must have been equal to 0. So that's what we're going to do. We're going to set each factor equal to 0. Now this first factor is useless. It does not give me any information about x. I can set it equal to 0, but that's not a true statement. Negative 2 does not equal 0. And then I proceed with the remaining 3 factors. X plus 3 equals 0, or it was the x minus 3 that equaled 0, or x minus 5 equal to 0, or all of them. And so we're going to isolate our variable. Subtract 3 from both sides of the equation. Add 3 to both sides of the equation. Add 5 to both sides of the equation. And this is what we have left. X is negative 3, or x is positive 3, or x is 5. So those are our critical values. And so we're going to place those on the number line. Negative 3, positive 3, and positive 5. Just so happens they're all in ascending order. So we analyze our inequality. And we see that there is no equal to present. So that means our endpoints will be open. We can take care of that now. Open on all of our critical values, which are endpoints. And we also take a look at the fact that this is less than 0. Less than 0 means negative. So we're looking for negative regions on our number line. Something that's going to make this statement true. So we have to test. We're going to test between a negative number and a positive number. We get 0. So we'll test 0. We could have tested 1. We're going to test 4, 6, and negative 4. So we have to consider the factored form here as we test. So we have negative 2, 4, negative 4 plus 3. Negative 4 plus 3, or 3 subtract 4, that's a negative. And negative 4 minus 3, that's a negative. And so we're going to get negative result here. Plugging in 0, negative 2, 0 plus 3, that's going to be positive. 0 subtract 3, that's going to be negative. So we're going to get a positive region here. And we're basically expecting the third region to be negative and the fourth region to be positive. But we're going to take our time and check. The third region, negative 2 times 4 plus 3 is positive 7. So that's a positive outcome. 4 take away 3 is positive 1. That's a positive outcome. So we're going to get a negative result here. And finally, we're testing 6. And I'm forgetting a region I'm so used to. So let's slow down. So used to 3 factors. And so we want to make sure this does not happen to us on the test. What about this factor? Okay, so all we have to do is adjust. Let's go back and plug in negative 4. Negative 4 minus 5 is negative 9. So we're going to get a negative here. And let's go ahead and check our work. Negative times a negative is a positive. Again, negative times negative is a positive. Positive times positive is positive. So this is a positive region. Don't remember what we had before. So now we're expecting positive, negative, positive, negative. Let's test our 0. Let's plug it in here. 0, take away 5. It's going to give us a negative. So here, negative. Negative times negative is a positive. Negative times positive is negative. So this region is indeed negative. And our third region, we were missing the minus 5. So let's plug in 4 times, actually 4 minus 5. That's going to give us a negative. Okay? So negative times positive is negative. Positive times negative is negative. And negative times negative is going to be positive. So this region is positive. And finally, let's test the fourth and final region. We have negative 2. And we're plugging 6 in here. 6 plus 3 is 9. That's positive. 6 take away 3 is 3. That's positive. And our fourth and final factor, 6 take away 5 is 1. That's positive. So we get negative times a positive and negative times a positive again. So this region is negative. remember, we are looking for negative regions. Less than 0 is negative. So these will be our shaded regions. And so in interval notation, let's include our endpoints again. And we know where the shading is, the negative regions. And so now open endpoints look like this. Okay? And so when we write our interval notation, open endpoint, not including -3, and going out to +3 and not including +3, united with this final interval, starting with 5 but not including 5, and going out to +infinity. So this shows us our answer. Solution sets both in interval notation as well as graphical notation. Okay. And now our 6th and final question. Well, I do have some more notes for you, but let's look at our 6th problem. -8 is greater than 2x minus x squared. Okay. So we want to collect all of our terms to the left. So I'm going to start with the leading coefficient. Or the leading term. I'm going to add x squared to both sides. I'm not going to place it under the constant because it's not a like term. I'm going to add that out front. What you do to one side, you do to the other. Since this is positive 2x, I'm going to subtract 2x from both sides. Again, I'm not going to subtract it under the constant because I want to collect like terms and that those are unlike. So I'm going to start a new column. And that takes care of everything that was both terms that were on the right side of the inequality. So now I get x cubed, or actually x squared, minus 2x minus 8 is greater than 0. 2x minus itself is 0. X squared minus itself is x squared, leaving 0 terms on the right. So now I have a trinomial that I'm going to factor. And when I look at my choices, x times x, first times first, in the FOIL process, 1 times 8, or 2 times 4. Last times last. That's how we get x squared. That's how we get 8. Looking at our sign rules, I need to assign a pair of factors, either the 1 and the 8 or the 2 and the 4. That's going to subtract based on this last sign on the constant to give me 2. Okay? And that's going to be this set of factors. So now I factor this trinomial, and I place my x times x in the first terms of each binomial, and I place the 2 and the 4 in the last terms of each binomial, and I need my sign rules again. This sign not only tells me I'm going to choose factors that subtract to the middle term, it tells me that the signs will be different. And I need the outcome to be subtraction. This 4 is going to control the outcome. So I'll make that subtraction like the middle term. And the other sign will just be different. Okay, so I have factored this. If I want to check, I check the product of the inner and the outer part of FOIL, inner times inner, and outer times outer, and that will give me my middle term. So now we are going to find our critical values using the zero product property, which says I set each of these factors equal to 0 and isolate x. At this point, we know either x plus 2 equals 0 or x minus 4 equals 0. Isolate x, subtract 2 from both sides, add 4 to both sides, and we get x equals negative 2 or x equals positive 4. Those are my critical value. Since I have 2 critical values, I'm going to divide my number line into 3 intervals. Negative 2 and positive 4. When we analyze our inequality, there is no equal to present. So the endpoints will be open. And greater than 0 means we're looking for positive solutions. Solutions that will make this product positive. So between a negative number and a positive number, we find the number 0. Beyond 4 is 5. To the left of negative 2 is negative 3. We can choose larger or smaller numbers, but we've chosen negative 3, 0, and positive 5. So we have to test. So let's test negative 3. Negative 3 plus 2. That's going to be a negative outcome. Negative 3 subtract 4. That's also going to be negative. A negative times a negative is positive. This region, this left region, is positive. And I suspect the signs will alternate. But let's check. Plugging in 0 in the 2 factors. 0 plus 2 is 2. 0 take away 4 is negative 4. So I get a negative outcome in the middle. On the right, let's plug in 5. 5 plus 2 is 7. That's a positive outcome. 5 take away 4 is 1. That's a positive outcome. Positive times a positive is positive. And looking back at our inequality, we are looking for positive outcomes. Okay? So we're going to graph those regions. And we're not including our endpoint. So now, when we graph using the interval endpoints, this is how it looks. Not including 4 and numbers larger. Not including negative 2 and numbers smaller. And so interval notation not including negative infinity, and going to -2, not including that endpoint, joined with the interval from 4 out to positive infinity. So interval notation and graphical form of the solution set. Okay? And so, although we didn't have a problem number 7 on our paper, I want to show you an example to wrap this up. Part A, we're going to be using the same trinomial, x squared plus 6x plus 9. And we're going to look at the case greater than 0. And when we factor this, we know the signs are going to be the same. Same could mean negative times negative or positive times positive. We look at this middle term to see how they're going to be the same. And we notice that they're both going to be plus signs in our factors. We also see a plus back here that also tells us we're going to be adding to get 6x. So we won't be using 1 times 9. However, we will use 3 times 3. So we'll place these into our binomials. X times x in first place, 3 times 3 in last place for both binomials. And using our sign rules, we're going to place the pluses. Okay, so that's a binomial squared. And so our critical values have been duplicated. It looks, we have 2 factors, but because they're identical, we're going to get the exact same critical value from each. So x plus 3 equals 0 or x plus 3 equals 0. We add 3, or actually 3 is already being added. So we're going to subtract 3 from both sides. That leaves us with x isolated to be -3. And we have the same statement, which means we really have one statement, x equals -3. So because we only have one critical value, the number line is going to be divided in 2. Around -3. And so there's no equal to present here. So the endpoint will be open. More than 0 means positive. So an open interval, and we're looking for positive. Numbers larger than 3 would be 0. Smaller than 3 would be -4. So we're going to test this out. -4 plus 3. It's going to be negative. And again, -4 plus 3 is negative. This is our positive region. That's what we're looking for. Let's test the other region. 0 plus 3 is positive. 0 plus 3 again is positive. This region also is positive. So we have shaded all real numbers except the number 3. So this is how this would look in interval notation. Starting with negative infinity, and going up to negative 3, but not including negative 3. United with starting with negative 3, not including negative 3, and going out to positive infinity. Okay, so that's our interval notation. We're going to take, and that came from part A, x squared plus 6x plus 9 greater than 0. And this is a binomial square, and we factored it this way. So let's move on to part B. Part B looks like this. Same trinomial, but this time greater than or equal to 0. Well, we know our critical value is negative 3. It's factored the same way. We get our same critical values. And we have the same interval, positive and negative. Actually, both of these were positive when we plugged in our numbers. That's not going to change. What is changing now, there is an equal to allowed. So we're going to have a closed endpoint. And we are looking for positive numbers. So basically, that's everything. From negative infinity, including the negative 3, to positive infinity. So that's all real numbers. And we write that in interval notation as from negative infinity to positive infinity. Now, let's look at a play on that. Let's look at the negative cases with and without the equal to. So we're going to do x squared plus 6x plus 9, this time less than 0. And we know all of the regions are positive, so I wonder what the graph is going to look like when we're looking for less than 0. So remember, when we factor this, x plus 3 times the quantity x plus 3 less than 0, we get a critical value of negative 3. We also get both sides are positive. And because there's not an equal to present, we don't get to include our endpoint. And we don't get to shade anything, not our endpoint and neither side of the endpoint. So there is no real solution here. No solution. And in the computer program, you might also indicate does not exist. The solution does not exist. Okay? And finally, part D. Same trinomial, this time less than or equal to 0. Same number line, same critical value, pluses on both sides. This time, because the equal to is present, we get to include our endpoint. However, because we're looking for negative results, less than 0, neither of these are negative. They're both positive. So the only thing we get to include now is the negative 3. So the answer is x equals negative 3. And in interval notation, we get to start at negative 3, and we get to include it, and we end at that same spot, negative 3. And so that concludes our presentation for polynomial inequalities. Thank you for visiting Math Made Simple by Professor Burnett. Please like and subscribe and come back for more videos. Thank you.